All right. So we're going to spend some more time with balancing chemical reactions today and talking about how we can predict how much product we're going to make out of chemical reactions or how much reactant gets used up. But first, couple random questions, some of which are pretty relevant. Do different colors of light always mean the same frequency or wavelength? The answer is yes. You can get, sometimes there's some things that can happen if you have a specific wavelength of light that's being emitted, say a blue color is being emitted, and then at the same time, a yellow color is being emitted. If the dots are small enough, if you've taken any art classes, you know, what do we get when we mix blue and yellow? Green, right? That actually does have a basis in the physics, except it's not that we're actually going to emit a green color when we do that. It's more to do with the way that our brain processes it. When it's small enough, your brain doesn't have the resolution, and so it kind of takes the average of two things. And that's why if you look at, it's harder to see it on modern screens, but if you take a magnifying glass and zoom in far enough on a television screen, then sometimes you can still see the individual pixels, the red, green, and cyan that make up the actual colors of the screen. And they basically, just by mixing them in different intensities, you get all of the various colors that your TV can display or that your screen can display. But it's more to do, the color theory side of it is more to do with the way the brain processes it. Because when we mix these two things together, we see both of them at the same time, which our brain interprets as being halfway in between those two wavelengths. But if you took that light and then you put it through a prism, you would actually see that barcode sort of figure show up where you actually have blue and yellow. But you actually have to, if the colors are actually mixed together, then you actually have to put it through a prism. And it is a little bit different when you're actually pulling it from a TV, because the computer that runs the TV is actually going to process the data. And so it might actually average those together. The old school CRTs actually had individual blue dots, yellow dots, and cyan red dots. They got mixed together. So you could actually physically see those if you got out a magnifying glass and looked at a color TV screen from the CRT era. I don't think they work like that anymore, but it might just be fine enough resolution that you can't see it. So try it sometime. Somebody asked about plasma. We're going to talk more about states of matter after the midterm. So after the midterm, which again is going to be a week from Friday. After the midterm, we're going to talk about some more things about molecular shape and polarity, and we're going to talk about reaction types and energy and kind of how all those tie together. Maddie?
Friday's a minimum day.
It's the Friday of midterm?
Yeah.
Where you guys hearing that from?
My dad.
It's on the calendar as we just checked it as midterms. But yeah, it is grayed out here. It does say minimum. It does say minimum day. I don't know how we missed that when we looked at that last week. We both stood there and looked at that and thought, oh, that would be good. So maybe if it is a minimum day on that Friday, then we'll take it on the Thursday. So you have the full time.
You do like the second.
How long is your class on a minimum day?
50 minutes, 40 minutes, 40 minutes.
I would just not.
I think we'll just do it Thursday. It won't be as bad as you're thinking it is. We might, and then I think that makes more sense because I would have to split up the test. Yeah, let me think on that, but probably not. I'm not adverse to the idea. I've done it before. It just never seemed to work out very well. So anyway, I guess while we're talking about scheduling stuff, For the rest of this week, I won't be here on Wednesday. In interview panel that I have to sit and listen to people say the same thing over and over again for 6 hours on Wednesday. Trust me, I'd rather be here. So I won't be here on Wednesday. You'll have a digital lab again this week, not spreadsheet based. But do bring your Chromebook or laptop, and it's basically going to have you play around with those 3D geometries and answer some questions, practice drawing them that we've been talking about. And so you'll be working on that on Wednesday and Thursday, and then I'll also have your practice test will be available for you on Thursday as well, to start working on. Was there anything else? Polyatomic quiz is going to be on Thursday as well. All right, so I think we're set up. We've got a lot of assignments going on this week, so I don't think it'll be a problem that I'm not covering new material on Wednesday, because you can use the time to catch up on other stuff, and I'll be back on Friday. All right. So we got to scheduling because I was talking about after the midterm for this question. We'll talk more about different states of matter and energy after the midterm, and that will make what I'm about to say make a little bit more sense. But basically, a plasma is what you get when you have atoms that have enough energy that the electrons don't stay bound to the nuclei anymore. Basically, if you heat it up enough, heating things up, warming them up, it's basically making the atoms vibrate faster, giving the atoms more kinetic energy. If you do that to a large enough extent, what you actually get is those vibrations can cause the electrons to just disassociate from the atom entirely, especially if everything's packed really closely together by gravity or by something else. So a plasma is basically a state that's kind of like a gas, kind of like a liquid, where the electrons are actually free to move around, almost like you can think of it kind of like a electron bath that these nuclei are kind of floating around in.
I'm gonna say like an electron suit.
Yeah, exactly. Yeah.
Not like the same concept.
No. So plasma in your body, it's another case of biology and chemistry reusing the same word in a confusing way. Blood plasma, I believe, is the solvent that your red blood cells float around in, with some specific proteins also added. Just the liquid, I think, is called serum, and serum with certain proteins in it, I believe, is plasma. But don't quote me on that because I'm not a medical doctor. I just know it's not the same as the state of matter. Yeah, basically. Here's another one that I don't know the answer to, but I can tell you that we're still doing lots of interesting research going into consciousness, and dreaming is really sort of an unexpected byproduct of consciousness to the extent that we can figure out what's going on. So there are some theories that it's the way that the brain processes short-term memory and sort of refiles them, like inside out. Basically, short-term memory is the memories that they had in headquarters, or whatever it was called. And then at the end of every night, when Riley goes to sleep, they flush them out to long-term storage. That actually is based on real cognitive science, but we don't have a conclusive reason why we need to do that, or why we forget them immediately when we wake up, or why they're so weird. But there's a lot of things about consciousness that are sort of just unexpected. But consciousness itself, actually, you could say, is just an unexpected byproduct of the way that matter interacts in our brains. The way that our brains correlate cause and effect and try to interpret that and apply that to larger scales kind of causes consciousness. And that's why basically the larger an animal's brain gets, the closer they are to being what we consider a human consciousness. Consciousness is not really a binary state. It's a spectrum, like most things. And so different animals that are more similar to our evolutionary history will also have similar layers of consciousness And that's why like, some mammals will also dream, even though we don't think of them as being human type consciousness, but they have similar ability to understand cause and effect in similar evolutionary history. So all that to say, neuroscience is a really cool field. There's a lot of interesting research going on in neuroscience right now, which is basically trying to take psychology and use biochemistry to explain aspects of psychology. So if psychology is interesting to you and science is interesting to you, neurology is a really interesting field, or neuroscience. Different schools use different terms for it. If the majority of the atmosphere is nitrogen and oxygen is most of what's left, why is CO2 such a problem? CO2 is not the only gas that's a problem. Does anybody know what it is about CO2 that makes it a what they call a pollutant of concern? What is it, Laura? It winds up as part of the atmosphere and it causes energy to get trapped in the atmosphere. Basically, there's a class of molecules that when they get hit with light, will absorb that light and turn it into energy and turn it into kinetic energy instead of light energy, which basically means you're going to warm things up. And water, CO2, and methane are all really big, what they call greenhouse gases, because of their molecular shape. Yeah, so CO2 is one of them, is the most common one. Methane's actually worse. CO2 is linear, but if you wiggle one of these carbons, you actually cause a little bit of asymmetry when you do that. And these things are constantly vibrating all over the place. It's not like they're actually connected with a stick. It's more like they're connected with springs. And different springs will absorb light in different frequencies. And so CO2 in particular, because of the way it vibrates, because of its structure and the strength of these bonds and its shape, it will absorb light in the infrared and in the, not in the visible region, but in the infrared region. And that actually causes it to trap heat. So light photons that normally would hit the Earth and then bounce back off out into space, don't bounce back off into space anymore. They get caught, which contributes to the overall warming of the atmosphere. And there's basically any gas where if it vibrates, it can cause a change in polarity, a change in where the electron density is going to absorb light in the infrared region. But all of our diatomic gases, like oxygen, just looks like that. Nitrogen looks like that. Those, because they're only two atoms, there's only one vibration that they can have. They can just vibrate in and out. And that's a vibration that doesn't absorb light in the infrared. And so they're not greenhouse gases. But small amounts of greenhouse gases can cause a big effect, especially where we are in the solar system and the wavelength of light that our sun puts out. All right. And then two questions that were really directly relevant. Were there any ways to visualize the structure of compounds before Lewis dot structures? Not really. Lewis dot structure, we still use, his name is still taught everywhere because it was so revolutionary. They basically didn't have a way to visualize these atoms or a way to predict what the shapes would be until Lewis dot structure. And they used that to confirm some things and then they use X-ray crystallography to confirm some of these structures. Leonora?
These models that are accurate, like the quantum modeling.
Kind of, not at the molecular level. That was more at the atomic level. But basically, yeah, they just thought of them as all being stuck together. Sort of as, I guess, kind of like the plum pudding model a little bit. If you just put 2 parts hydrogen, 1 part oxygen into a stew, and that's water.
So it's like not of the structure, but of the idea.
Yeah, it was basically, they knew that atoms and molecules, or the molecules existed, but they didn't really have an idea for how they were attached together. Which makes sense because until we had ideas like quantum mechanics and covalent bonds, there really wasn't any way to describe that. is there any compound that can be stable when you switch it out? So if we switched out the center atom here, we get something that doesn't look very stable, because this is going to wind up with an oxygen with a +2 charge and a carbon with a -2 charge, right? But there are a few compounds that are either relatively stable if you swap things out, or stable enough that we actually can observe them. In particular, hydrocyanic acid. We came to the conclusion that this was our best structure for it, but you can actually have an isohydrocyanic acid, which is the isomer where you basically switch these two. It's not as stable, because we do get a +1 formal charge on a nitrogen and a -1 formal charge on the carbon, but it's stable enough we can actually observe it. We can actually see this compound. If you let it warm up though, it'll spontaneously rearrange itself. So there are some cases, and there are some cases I'm not able to think of one off the top of my head, but there are some cases where you have some isomers that are almost as stable. I guess you could look at ethanol versus dimethyl ether again. It's really common when you get into organic chemistry, because there's lots of ways you can arrange these atoms where everything has a formal charge of 0 still. So this is ethanol, drinking alcohol. This is really stable. This one is not as stable, but it's definitely still stable enough that we can bottle it and store it and use it as a solvent. Same formula, different Lewis dot structure, totally different compound. Different properties of the compound. When we talk about polarity, it'll make more sense why that is as well. But yeah, you see a lot of that in organic chemistry, because in organic chemistry, when we talk about these Lewis dot structures, we talk about them basically in the context of a carbon with 4 bonds has a charge of 0. And so there's a lot of different ways, basically any way you can arrange it so the carbon has 4 bonds and oxygen has 2 bonds, those are all going to be almost equally valid.
I feel like everything you talk about is sort of affected.
Well, it's because it's my favorite class. I took a lot of organic chemistry. My research was in organic chemistry, and I'm teaching organic chemistry right now. So, it's basically organic chemistry is the first chemistry class where we don't say things like, well, we're going to teach you the general rule for now, but we're going to have to unlearn it later. Like same way with the Lewis dot structures, right? Where we said, well, I'm not going to ask you about the D block because we're not going to go into that much depth on the D block. Organic chemistry is the first science class where we don't have to say that really. We can actually approach everything at the full level of intensity and rigor. And you take that before you take other similar classes. So it's a common class to take your second year of a science major. Plus, you actually get to learn about scientists that are still alive in some cases. Like we just covered the most recent Nobel Prize winner who's won his second Nobel Prize. We actually covered the material he won his first Nobel Prize for in OChem 2 last week. Which is kind of fun. We're actually getting like cutting edge enough that's people that are still alive that are winning Nobel Prizes, as opposed to, you know, Isaac Newton from 400 years ago. All right. Let's do some practice balancing these. So balancing chemical reactions. What's the general gist of what we're trying to do when we're balancing reactions? Move stuff around. You got to have the same number of atoms, and they have to be the same type of atoms too. Right? So if we have 1 phosphorus on the left-hand side, we want to have 1 phosphorus on the right-hand side. We can't have matter disappearing, and we also can't create matter out of nothing. So with that in mind, take a couple minutes and try some of these, see if they can all. I don't think there's any in here that are too tricky. Sometimes have asked questions that are trick questions on accident. Oh, there's one that I fixed. You notice the font on that 2 on the NO2 is different because it was impossible to balance before I fixed it.
Will you ever give us ones that are impossible to balance just for us to like realize that they're impossible to balance?
Not on purpose.
Okay.
And really, if you get a reaction that's impossible to balance, then either one of your compounds isn't right. Like for instance, in this case, it was NO2, not NO. One of the other things that can happen though is you could be missing another product or reactant. All right, let's look at this first one. So one of the trickiest things when you're first learning how to balance reactions, it seems like if you don't have like a set process to go through, it can seem a little bit daunting. Like, well, where do I start? Basically, just pick an element and check to see if it's balanced. Everything has to be balanced at the end, right? So it actually doesn't really matter where you start. By convention, I generally pick something that I don't have very much of. You start by balancing the phosphoruses, and then whatever you have a lot of might wind up taking care of itself if you balance the other things first. That doesn't really help us in this case because the phosphorus is already balanced, right? So one other thing we only have one of is oxygen, which is also already balanced. But we can look at the hydrogens. The other thing that you kind of want to avoid is if you have one element that's in 2 different products, sometimes that's going to make it trickier to balance. So I'm going to not touch the chlorine yet and see if it takes care of itself. So 2 hydrogens here. The only place hydrogen shows up over here is the HCl. So we've got to have a 2 there. And now, if we double check the chlorines, we have 5 chlorines on the left and we still have 5 chlorines on the right. Right, so in general, and that is the hardest place to start is if you have the same element that shows up in 2 different products or 2 different reactants, because you have 2 ways of changing how much of that atom you have, right? And it's not always obvious to see. So generally speaking, leave those till the end and see if they take care of themselves. How about down here? The top one? Yes. So if you don't put a number in front of it, you can assume it's a 1, or you can on the test. I'm going to leave a blank in front of each of them so you can write 1. But if you don't write a number, it's assumed to be 1. So as soon as we put that 2 in front of the HCl, it was balanced. So there's going to be 3 chemical reaction questions, and each of them is going to have you balance the reaction first. Basically, the first thing you do when you're given a chemical reaction is see if it's balanced, and if it's not, balance it. So it'll be a total of, I think it's 4 points on each of those, so 12 points out of the midterm is going to be balancing. So here we've got another kind of tricky case, right? Nitrogen shows up in 2 places on the right-hand side, so don't touch nitrogen yet. Copper looks good already. Hydrogen, we know we've got to have at least a 2-to-1 ratio in here, right? Because we're making water. The only place hydrogen shows up over here is as water. And we only have nitric acid on the left-hand side. So we know that we have to have at least 2 of these. And whatever happens, it's going to be a 2-to-1 ratio of the nitric acid to water, because that's the only place hydrogen shows up on the reactant side and the only place hydrogen shows up on the product side. So they're going to always have to be in that 2-to-1 ratio, even if we have to go back and change things, which we are, right? So what could we do? Copper looks good, hydrogen looks good, but we have 3 nitrogens on the right-hand side and only 2 over here. So we know we have to have an even number of hydrogens because of the water. But we also know we have to have a multiple of, well, not necessarily a multiple of 3, but we've got to do something else. It's got to be more than 2. So let's try the next even number. Try 4. Now that means we're making 2 waters. We have 4 nitrogens to work with. If 2 of our nitrogens are in the form of nitrate, what does that do? Copper is still good. Hydrogen's good. Did that fix our nitrogens and oxygens? So now we have a total of 4 nitrogens on the right-hand side. Got 6 oxygens here. 7, 8, 9, 10, 11, 12. Total of 12 oxygens. 12 oxygens over here. And so if it feels a little bit like a glorified, more confusing guess and check, it kind of is. Plug stuff in, see if it works. There is some amount of method to it, and when you take linear algebra, which is not as easy as it sounds. Linear algebra is not algebra 1. Linear algebra is using matrices to represent algebraic functions and solving them. And so it's a 2nd year math class, 2nd year in college math class. You usually take after you've taken multivariable calc. Michaela? So there's 2 here and then 2 there. Exactly. So that's what I mean about when you have the nitrogen and the oxygen showing up in 2 different, oxygen's actually showing up in 3 different things. Those are really tricky to figure out. Those are always going to be your biggest hurdles. There's a total of 6 oxygens here, plus another 2, plus another 4, for a total of 12. So there is actually a mathematical way. If you do it with matrices in linear algebra, there's a mathematical way that you can plug this in and actually get the calculator to solve it for you, basically. But generally speaking, once you get the hang of this, it's actually more trouble than it's worth to actually write out a matrix and write out all the different algebra expressions. Sorry, say that again. No. So this 2 subscript is applying to the nitrate. So there's 2 nitrates for every 1 copper. That's me.
That time is by 3, right? So it'd be 12.
Exactly. Yeah. So these coefficients are applying to the entire molecule. So this is nitric acid, and we're saying 4 nitric acid molecules, 4 of this entire thing. Leonora?
In the event that we wanted the 2 to apply to the copper, we do double parentheses, so we would have the parentheses that are originally there.
You could do square brackets or something like that if we wanted to say we had 2 of that entire thing. Yeah. We do nested parentheses in chemistry, and they work just like in math. But so, Leonora, we would only do that if there was some reason that we needed 2 of this entire thing. For the most part, we would do that by putting a coefficient in front of the whole thing, because that would mean the same thing, right?
Individually and not within the reaction, would we not do that?
Correct.
Thank you.
No problem. All right, so that's B is the hardest one up here. If you manage to get through B, the rest of these should be relatively straightforward. Hydrogen and iodine reacting. We have 2 hydrogens on the left-hand side. We only have 1 hydrogen on the right. And we only have 1 product, which makes things easy. Balance your hydrogens. That also took care of our iodine at the same time, right? Most of the reactions you're going to balance are going to be more like 1 and 3, or at most 4. This is kind of an exception as to how complicated it is. How about iron plus oxygen turning into iron 3 oxide? What do we know right off the bat? We know that the iron oxide and the iron are going to be a 2-to-1 ratio. Vinny, what'd you say? The right side's going to need to be even because we've got an odd number of oxygens in this compound, right? But we can only add our oxygens 2 at a time. So it means we need an even number of oxygens on both sides. So if we do that, anybody know what this reaction is? Oxidation, iron rusting. You leave iron exposed to oxygen, it turns into iron 3 oxide, better known as rust. Interestingly enough, we don't actually find iron as a metal. When we mine iron, we actually mine iron 3 oxide for the most part. Because we have enough oxygen in our atmosphere that you almost never see metallic iron because it oxidizes too easily, it rusts too easily. So when we find iron, it's in the form of iron ore, which you then have to smelt down to reduce the iron. And this is kind of fun. Anybody know what you use to smelt iron ore? A furnace and a heat source, but ideally coal, if you've played your Minecraft. So here's another balancing one. We can balance that reaction. Iron 3 oxide, or iron ore, if it's in its mineral state, plus carbon turns into metallic iron and carbon monoxide. And we can actually balance that. And actually, I think we get carbon monoxide and CO2. I think we have to do that in order for it to balance. But yeah, so technically anything you can burn, you can smelt iron with. Coal works really well because you don't have to supply additional oxygen to it to keep it burning if you're in the presence of rust. And so this is actually one of the first chemical reactions that humans discovered after fire was basically this, and this caused the transition historically from the Bronze Age into the Iron Age, was this reaction becoming commonly known.
When they find iron, is it inside roaster too?
Typically, yeah.
How did they do that?
Because it's not just oxygen that can cause iron to rust. Anything that has a stronger electronegativity than iron can basically steal electrons from it. So like something might be iron nitride, it might be iron sulfide. There's a lot of different minerals that are iron ore. Not all iron ore looks like this. Some iron ore has different colors and chemicals in it.
Copper is complicated.
It does, but copper is more stable as a metal, so you can find copper as a metal. Maddie?
Can you go over the 10-page problem on our midterms is gonna be like a complicated one? Can you go over like the fraction one? Because I saw like fraction.
So that's a good question. It is sometimes you will actually see chemical reactions balanced with fractions. I don't really like that because we don't have fractions of molecules. So I'm not going to ask you any questions, and I don't want to see them as fractions. But in theory, if we're just talking about ratios, we could divide each of these by 4 and get iron plus 3/4 oxygen goes to 1/2 Fe2O3. But that doesn't really make a whole lot of sense when we're talking about molecules, right?
I saw one like that on the midterm test, so I'm just.
Probably not on my midterm practice test.
Okay, I didn't like this one.
Maybe show me. But you said it was on number.
It was this 10 page, like the tricky one that you said, like that's the thing.
Yeah. All right, let's pull that up real quick. Let's look at that and see what's going on with that. So basically the reason that you would write it something like this is if we wanted to look at the reaction relative to 1 mole of iron. So it makes the most sense to do it all with whole numbers, but then it's for every 4 moles of iron. We have everything balanced. When we start talking about energy, a lot of times we want to do it relative to 1 mole of iron. And so in that case, we might just take the balanced reaction and divide everything by 4 like I did here. And so if that's on the practice test, it's probably because I asked you something about per mole of one of the reactants. There's probably a per mole part in there. So let me pull it up and we'll double check it. And you know what? Y'all asked the questions in the right order. It was last spring that we split the midterm into 2 pieces. And we did that because of the timing issue. So I think we did split it up last spring here. So it's already set up to do that. So maybe we will do that since it's a minimum day on the Friday. It'll be basically parts numbers 1 through 6 on day 1, and then 7 through 10 on day 2. Which will be all of the stuff we're going over now. The balancing and the stoichiometry would be on the 2nd day then, and the wild card for that matter. So, relevant question. There it is. Ah. So this is the other way of writing. If we're talking about specific isotopes, we actually write it out in the isotope notation. So this is not the balancing. That's actually saying that it's uranium-235. It's a specific isotope of uranium. So it's not saying you need 235 uraniums. It's saying that the uranium that you need is the one that has a mass number of 235. So 92 is, say it again. Number of protons, yeah. So the bottom number, down and to the left, is always how many protons you have. Up and to the left is how many is protons plus neutrons. You guys remember doing that when we first learned about isotopes? So we frequently, if you look at this, this doesn't look balanced, right? According to the way we're doing it right now. But if you take all of the numbers at the top left, you take all the mass numbers and add them up, it is balanced. So with nuclear reactions, you're actually balancing your total number of protons plus neutrons. But because they can split up and different reactions can happen, it's like, for instance, if you hit uranium-235 with a neutron, the neutron can get lodged inside that nucleus temporarily and causes that entire nucleus to fragment. And so you wind up making krypton and barium and 3 more neutrons. So what this is saying is in a nuclear reaction where the nucleus changes, the way we balance it's a little bit different. But since we haven't learned that on this problem, I was just using this notation to give you the already balanced reaction. And then it says, gives you an energy in kilojoules per mole, how many energy can be produced from a certain amount of soil. So it's basically, you have a balanced reaction, and this is bringing in energy into it, which we haven't really talked about. All you really need to know, though, to solve this problem is that kilojoules is an energy unit. Because it doesn't actually ask you to do anything with that. It just says how much energy can you produce. Right? So you don't actually need to do that to use that kilojoules for anything, which is part of what makes this a wild card question. By the time we get through the nuclear chemistry unit, this will actually seem like a piece of cake because you'll have more experience with it. It won't be a wild card question. It will just be one of the regular questions. But I guess while we have it up, you can also look at Michaela, to answer your question, where does Michaela's not in here anymore, but yeah, there you are. This is how it shows up on the 3 chemical reactions. I'm going to have you balance it and then do some math with it. Sorry, I caught you in the middle of getting past. All right, so how are we feeling about balancing? A little bit wishy-washy, a little bit guess and check, but you know it's going to be whole numbers. And I'm not going to ask you anything where you have to get into double digits. There are some reactions that have double digits in the coefficients. We won't get into that for this class. Well, at least not yet. All right. Let's do one more. Another combustion reaction where we're going to burn stuff. This is not butane, this is propane. C3H8 plus O2 makes CO2 and water. So, what do you know about CO2s? 3 to 1. 3 carbons over here, we got to make 3 CO2s. 4 hydrogens on the left, or sorry, 8 hydrogens on the left means we can make 4 waters. Which means everything, our oxygens are even over here now, right? Which means 5. 2 from turn into the water, and another 3 turn into CO2. So just double check the counting when you're doing these. All right, so if we're trying to, I heard somebody say something about it. Also, it's weird that combustion also produces water. All combustion reactions also produce water. The most oxidized form of hydrogen is water. So when you take something with a bunch of carbons and hydrogens and you burn it, you're always going to make a small amount of water. Yeah, basically. If I was being really careful with my signs here, or my phases, this reaction happens in the gas phase. This is actually one of the reasons why contrails form behind planes. Is because if you have a plane flying through a part of the upper atmosphere that's already saturated with water, it doesn't look like there's clouds there. But if you take that air, heat it up a little bit, run it through an engine, burn something, add a little bit more water, when you do that, that can start a process of cloud formation. So that's one of the things that people that are, I don't know if chemtrails is still a common conspiracy theory, but basically, part of the evidence, if you want to call it that, for chemtrails was basically when a plane flies through the sky and then a cloud formation forms behind them. There. But that's actually exactly what the science would predict. You take that saturated system, disturb it a little bit, add a little bit more water, and that's enough to start the cloud formation. Once it starts in one place, it'll spread until all the available water is condensed into a cloud.
I believe that could be used to like, for like, if like, say for example, that was an accurate theory and people, or like the government did want to like enhance collaboration, could they like think that people would actually think that
You can do that, and actually, in the several days after 9/11, air traffic worldwide was grounded because they were trying to figure out security stuff and figure out what happened. So there actually was a period of a few days in late 2001 where we had 0 air traffic for 2-3 days, and we actually did see a difference in the way cloud formations formed. It is so one of the theories that I've heard is, well, the government's using chemtrails to try and create clouds to try and combat global warming, which sounds like it might make sense until you think about when was the last time a politician did something without trying to claim credit for it. So there's not a whole lot. Plus, water, increasing the amount of water in our upper atmosphere is a problem because water is a greenhouse gas, so it actually would make it worse.
Isn't like the opposite of that, people think like, they do that not to combat global warming, poison the air.
That was the original theory from back in the 70s, was that they were using chemicals in planes to distribute mind control drugs to the population. But again, with a little bit of critical thinking, is there an easier way you could distribute mind control drugs to most of the population in North America? Water supply would make a lot more sense, right? Or food, something like that, which you still wouldn't get people that are living off grid, but there's other ways to do it. Basically, and because there's nothing about the cloud formation that can't be explained by this. There's just not a whole lot of reason to go that kind of out there. But it is definitely still a common conspiracy theory I hear about. Jenny?
Does that mean that water would be good insulators in this form because it's a greenhouse gas and gaseous form?
It's a good insight, and actually we do use water in, so one of the big problems with designing a spacecraft that could fly, that could carry humans from Earth to another planet, is that all the radiation that you get when you're outside the Earth's magnetic sphere, basically would wind up causing, huge amount of radiation exposure. One of the ways that you could combat that is by encasing the living quarters in water. Because the water acting as a greenhouse gas is going to absorb a lot of that high energy light that would normally cause cancer. And then you just wind up with irradiated water, which actually calms back down really quickly because it's just basically warmed up for the most part.
Water also
Yeah, for similar reason. It's got a really high specific heat, which we haven't talked about yet, but basically it takes a lot of energy to change water's temperature relative to something like a metal. And so it is a good thermal insulator because it takes extra energy to get it to get really hot and to get it to go through a phase change. So yeah, so nuclear power plants use water. Basically, all a nuclear power plant is, it's the same exact technology as a coal power plant. It's also really similar to the same technology as a steam engine. Basically, boil water and you use the water to spin a turbine. And that turbine is just hooked up to a magnet inside of a coil of wire, and that generates a current. Nuclear power plants work the same way. They just use nuclear fuel rods to boil the water and then use the steam to spin the turbine. So basically all power plants, as they are currently designed, are basically just steam engines. All right. So why are we spending so much time balancing these reactions? Well, one, it doesn't make a whole lot of sense to say to not have them balanced. It makes more sense to have them balanced, right? But it also allows us, if we have an amount of one of our reactants, it allows us to actually predict how much product we can make too. The thing is, we can't just say, okay, for every 1 pound of propane, we can make 3 pounds of CO2. Because CO2 molecule doesn't weigh the same as a propane molecule. So if we're going to use these ratios, we balance them in terms of atoms or molecules, right? So if we're going to actually use this to predict how much of a product we can make, we also want to be putting our amount not in a mass, but in moles. So we're going to, a huge chunk of these problems is figure out how much starting material you have and then put it in moles. So if we have 5 pounds of propane, how many moles of propane is that? How are we going to figure that out? A lot, yeah. If we have 5 pounds, what's a roadmap look like? What are we going to convert pounds to? Grams. Because once we're in grams, we can do what? We can get to moles. We only have one tool to get to moles at this point. Well, I'll teach you some more. But for now, if we want to get to moles, we've got to get to grams first. And once we get to grams, we can use the periodic table to figure out how many grams per mole something is. So 5 pounds. What's our conversion for pounds to grams? A pound bigger than a gram or smaller than a gram? Bigger. So it's going to be a lot of grams to 1 pound. I believe it's 453.59. Thank you. You don't have to have that memorized though, because you're going to get a fresh conversion sheet attached to the back of your test. You just have to know how to use it. You're also going to have a periodic table, Isabella? Yep. You'll also have a periodic table, plus you'll be taking the test in here, so you'll have the periodic table on the wall and in front of you as well. How does the periodic table help us here? Say valence electrons, but not for this particular case. If we want to go from grams to moles, what do we need? The atomic mass of everything, right? So we're specifically talking about 5 pounds of the propane. So we add up all the pieces of our propane. So 3 carbons, and each carbon is 12.011 gram per mole. and 8 hydrogens, and each hydrogen is 1.008 grams per mole. Which I think is going to give us 44.1 ish. Somebody give me some more sig figs.
44.097.
Thank you. So if we want to get our atomic mass or molecular mass, we just take all the atomic masses of all the pieces and add them together. So 3 carbons and 8 hydrogens added together gives us 44.097 grams per mole. And that means for every 44.097 grams, that's 1 mole of propane. It doesn't matter if you remember this is called propane. Beside the point, as long as you know what the formula is, you can do this now. So we get something about 50. Just under 50, 49 something, 51. So I didn't give you, I gave you only 1 sig fig technically, but for the sake of doing this, let's say that it was 3 sig figs. So we keep 51.4 moles propane. So why does that help? Exactly. Think about my weird, we parted out the butane to make sleds out of the car doors analogy, right? If we're going to part this out to make CO2 out of it, we know that that's going to be in a 3-to-1 ratio. For every 1 molecule of propane, we can make 3 molecules of CO2. Or for every 1 mole of propane, we can make 3 moles of CO2. So basically, the whole point of getting everything into moles and balancing this is because it's going to allow us to convert between different compounds all of a sudden. Because we can say, and we'll do some analogies with recipes here in a minute too, if you're not seeing it yet. For every if we have 50.4 moles of propane, every time we burn 1 mole of propane, we make 3 moles of CO2. And 4 moles of H2O. So depending on what we care about, so usually the way these questions are worded, we're going to care about 1 specific product. So for instance, let me go back to the problem here. So the way that these get written on the test is, here's your reaction. Balance it. Figure out how many moles you have, one of your reactants, and use that to figure out how many grams of product you can make. Right? So the balancing is going to be where that conversion comes from. The conversion that allows us to go from moles of one thing to moles of another. And you're just going to take the coefficients, because we balanced it specifically so that we could take these coefficients and do this, and it would make sense. So if, just make the numbers work, if this is a tricycle, every carbon is a wheel. Every time, if we take all the wheels off of 50 tricycles, how many wheels do we have? 150, right? Because we can say for every 1 tricycle, we can get 3 wheels. That's all these coefficients are doing. Right? And so that this has a technical name. that probably is Greek. I don't actually know where it comes from. Stoichiometry is the big, long, scary word that just describes this. Balancing a reaction and using the coefficients as a conversion. All right, if you know how to balance the reaction, all we have to do is get things to moles. Once you get them to moles, we can do this. All right, so let's do another example of something that's not chemicals, because chemicals make it weird and abstract. Michaela? So it depends on what the question's asking. If I said in the question, how many moles of CO2 can you make, then it doesn't really matter that you also make the water. All I'm asking about is the CO2. I could also say how many moles of water would you make, and it would be a 4-to-1 ratio. So you can combine these coefficients in any way that you want. Right? So we can say, if we're trying to figure out how many moles of water, we would just say, okay, for every 1 mole of propane makes 4 moles of water. If I wanted to know how much oxygen was going to get burned up, I could do the same thing, except I'd be for every 1 mole of propane is 5 moles of oxygen used. Right? So you can actually combine these coefficients any way that you want, because all of this is happening simultaneously. Isabella? Yep. 3 of them. But one of them is going to be easy. I'll show you in a second. Destiny? Yeah, so let's follow that logic. If we actually want to know how many grams of water it's going to make, we can do an atomic mass calculation. Say, okay, for every 1 mole of water, that's 2 hydrogens and 1 oxygen, so about 18 grams, right? So it just adds one more step. If we're trying to go from grams of one reactant to grams of a product, we start by going grams of the reactant to moles of the reactant, moles of the reactant to moles of product, and then we can just do another atomic mass calculation as well. So it just adds one step. All right. Let's do something a little bit more concrete to wrap our heads around this. So let's say we're making a cheeseburger. Food analogies work really well in chemistry. So let's say in order to make a cheeseburger, I guess this is my perfect cheeseburger at home. You need a patty, a lot of cheese, and 2 pieces of bread. That's the raw ingredients for what's in order to make my cheeseburger. Obviously, proper sauce plays a big role as well, but we won't get into the specifics there. For my money, if you take some of the Chipotle Cholula and you mix it with blue cheese dressing, it makes a really good spread for burgers. But that's my personal preference. Does it matter if it's balanced or not? You're not going to be able to make my perfect cheeseburger if you don't have 3 slices of cheese, right? So the balancing comes into play when we're trying to figure out how much of something we're going to use or how much product we can make. So let's say I've got a whole freezer full of frozen patties, and I've got an entire bag of buns, but I only have 13 pieces of cheese. How many hamburgers can I make? Everybody knows how to do that math, right? It makes a lot of sense, but for some reason, when I put it into chemicals instead of pieces of cheese, everybody loses their mind. And that's fine, that's normal. Chemicals are weird and abstract. We're getting used to them. But that's the basic math that we're going to do. It's the logic that gives people trouble with it. It's totally simple to think about, oh, I'm using up these slices of cheese. How much can I make? I want you to keep in mind that's the same logic as what we're doing with stoichiometry. If we might run out of one of our reactants, we're just going to keep track of how much am I going to be using? How much product can I make? So let's say, let's make it a little bit more complicated. 1 patty plus 3 cheese plus 2 pieces of bread. Let's say I have 15 patties, 42 pieces of cheese, and 38 pieces of bread. How many cheeseburgers can I make? One really large one. You know, if you call them ahead of time, In-N-Out will still make really, really big burgers for you. We had to call and order it separately, but when I was in high school, we got my friend a 20 by 20 from In-N-Out for his birthday, which was big. They had to lay it down sideways, and it took up a whole cardboard carton. It was delicious. So with this in mind, how many hamburgers can we make? What are we going to run out of first? And how did you figure that out?
42 divided by 3.
42 divided by 3 is 14. So what you did the stoichiometry in your head intuitively. Because what we can say is, okay, let's say 42 pieces of cheese. And every 3 pieces of cheese is 1 burger. And we get 14 hamburgers possible. We do the same thing with patties. That's 1 to 1. We can do that math in our head, right? For every 1 patty, that's 1 hamburger. Then last but not least, let's think about bread. For every 38, we have 38 pieces of bread. For every 2 pieces of bread is 1 hamburger. 19. So how many hamburgers can I make? You pick the smallest number, and that's how many you can actually make, right? Again, for whatever reason, this is going to sound silly when we're talking about hamburgers, but I guarantee you at least one of you is going to do this on the test. For some reason, people do this math, and then they'll take all the answers and add them up. I have enough cheese to make 14 hamburgers, and I have enough patties to make 15 hamburgers. Therefore, I can make 29 hamburgers. Don't do that. That doesn't make any sense, right? Everybody's laughing because that sounds really silly to do that when we're talking about ingredients for a hamburger. But again, for whatever reason, as soon as I turn it into propane and oxygen, everybody freaks out. It's the same logic. Think about what are you using and what are you making? Are we adding something? We're making hamburgers by using reactants, right? Every chemical reaction works the same way. You use reactants and you make products. Figuring out how much product you can make is as easy as figuring out what's going to run out first, and then use that to figure out how much product you're going to make. Okay, whatever we're going to run out of first, we call that the limiting reactant. Because it's going to dictate everything else. Whatever you run out of first, that's your bottleneck, right? As soon as you run out of it, no more hamburgers. So it's our limiting reactant, and it's going to be what stops it, everything else. It's the reactants that we have left over are called excess reactants. Excess just means extra, right? So both the bread and the patties are excess reactants. If we want to know how much excess reactant, we say, okay, well, what's going to be left over? In that case, we might say, okay, I'm going to use 42 slices of cheese. For every 3 slices of cheese, 1 patty gets used. So when we do that, we get 14 patties used, right? So how many do I have left over? 1. The logic, again, the logic is really easy when we're talking about hamburgers. If you want to know how much excess reactant you have, you figure out how many got used and you figure out what you started with, and you just do a subtraction. We started with 15 patties. And we used 14 patties. 1 patty excess. How much bread is left over? That one's a little trickier. Just because it's not a nice eaten in 2-to-1. But if we have, we're going to do the same thing we did here. 42 slices of cheese. Every 3 slices of cheese is 2 pieces of bread used. So 14 times 2, 28. Bread used. And we had 38 to start. So we're going to have 10 pieces of bread left over. Yeah, 38 pieces of bread. That's probably close to 2 loaves. If we're just talking about white bread. Who makes a cheeseburger with white bread? All right. So you can see how I can ask word problems like this. And these actually kind of look like word problems that you might have had in algebra at some point, right? Where they try to take y equals mx plus b and actually put some stuff units to it. It's as easy as that. Trick is when we're dealing with moles of propane versus moles of CO2, it gets really easy to confuse yourself. So I want you to pay attention to, am I making it or using it? It's on the product side, I'm making it. We're adding that. If it's on the reactant side, you're using it up. And you can use these, you can basically stick used or produced on the end of our stoichiometry coefficient or conversion as a way to keep track of that. Yeah. So let's look at the test now. So like I said, there's going to be 3 of these. There's going to be an easy one where I already give you everything in moles. So balance it, figure out how many moles of one of the products, and I'll specify which product. So in this case, it's saying how many moles of lead 4 hydroxide could you make? So you don't have to do any atomic mass for this. Don't overthink this one. Number 7 is going to be really math light, because all you have to do is figure out how much gets used, what's running out first, and how much product you can make. And everything's already in moles. And then I'm going to ask you one that's in grams. The one in grams, I'm not even going to make you figure out the limiting reactant. I'm going to just tell you you have excess HCl. So take your grams, turn it to moles. Well, balance the reaction first. And take your grams, turn it to moles of tin. Moles of tin to moles of tin 4 chloride. Moles of tin 4 chloride to grams of tin 4 chloride. And then the last one is going to be an excess reactant. We haven't talked about concentration yet. That's going to be on Friday. We're going to do concentration units. So the units look weird here, but for now, all you have to know is it's a way to find moles. So if you have these 2 solutions, what's gonna run out first, and what's your concentration of the excess reactant. So telling you right off the bat, those are your 3 stoichiometry problems. Right? One's gonna be easy, moles to moles. One's gonna be grams to grams, and one's gonna be an excess reactant question. Feel it?
It would be just whatever you balance it like in front of them.
Yeah, so you see the blank space that I left here for you? You would just fill that in. So don't get hung up on the milliliters for now, because we'll talk about that on Friday. All right. So Friday, all we're gonna do is more practice with stoichiometry, and we're gonna add in concentration units, and that's gonna be it. And that's gonna be everything that's on the test. All right? Have a good day, everybody.